Hello and welcome to this clip which attempts to take you through a few tips and hints about how to deal with harder applied A-level calculations. You know the type I mean. They'll be in your RPA paper or in your EEE paper, and they'll suddenly be or appear to be about something that might be unrelated to RPA or might look like you haven't studied it before. And really all they're doing is asking you something fairly straightforward but wrapping it up in a new situation with an unusual set of data perhaps. So what I'll do is I'll take about 4 or 5 examples and take you through how to work them. But first of all, let's have a think about what you need to do to actually get yourself in the right place mentally to deal with one of these calculations when you're facing it in the real thing. So try to bear these in mind whenever you're approaching a tough-looking question, and hopefully it'll keep you on top of things and stop you from getting to the dreaded panic mode. So more often than not, you'll have enough data to work out the moles of something. That would be the good place to start. At least it gets you moving then. So there might be some clues, or there will be some clues in the body of the question. They will give you everything that you need to know to get started. Once you've identified them, it's well worth highlighting or underlining them so you can come back to them a bit later. It's also a really good idea to read the question one more time before you begin to make sure you haven't missed anything, just to check that there's no other information that you need to know that you've overlooked. Okay, so let's get started on a typical example of one of these types of questions. So the first type of harder question that you'll come across would be percentage yield. Here's a typical one. It's obviously an off-spec reaction because you don't have to do saponification or soap-making reactions for OCR. It'll be nowhere in the spec. So first thing you do, take a couple of deep breaths and think, okay, they've given me a reaction I'm not unlikely to have seen before, excuse me, and therefore I have to think about it a little bit. In fact, it was so applied that I had to stop the tape there and go and get myself some water. So, now I've sorted my voice out, let's have a look at what they want us to do. The first thing is they say 56 tons of C15H24O6 reacts with excess NaOH. Find the expected maximum yield in tons of both products. Now in brackets it tells you that 1 ton equals 1.0 times 10 to the 6 grams. That grams obviously means that somewhere along the line you're going to have to do moles equals mass over MR. In addition, the same sentence talks about excess NaOH. So excess means that you actually have more NaOH than is needed. The likelihood is that you will not have to work out the number of moles of NaOH that you'll need to use. So it says find the expected maximum yield in tons of both products. So that means both of these here have to be worked out. So let's get started. So we've got moving by working out the MR of C15H24O6. That's likely to get a mark. So now we've got the number of moles of C15H24O6, we can work out the number of moles of each product, which gets us a bit closer to working out the maximum yield in tons of both products. So all we really have to do is multiply up 186,700 the right number of times. I'm just going to go and adjust what I put underneath each one because I've realised I've misprinted it. Give me 2 seconds to get that sorted out. There we go, that's better. Right, so what we've got to do now is to work out what those number of moles of ethanol and the number of moles of the other product would be in tons. So in other words, we're working out what is the maximum amount we'd expect from 186,700 moles of C15H24O6 on the left-hand side of the equation. Okay, so as you can see, it's a simple case of doing moles equals mass over MR and then rearranging and then converting for tons, because that's the unit they want us to give the answer in. So now let's have a look at the next part of the question. So, what they'll do now Sorry about that voice malfunction. What they'll do now is give you the actual amount you'd get as opposed to the amount you'd expect to get. So you expect 25.8 tonnes, but then they tell you that in reality you only get 17.4. So what you've got to do now is work backwards from the percentage yield and try and find out what the percentage yield would be if you have this new amount. So in reality what you're doing is you're dividing the actual amount you get by the amount you expect to get and then expressing it as a percentage. So let's have a look at the next part of the question. So this one is a slightly different approach. It's just rearranging the percentage yield equation really. So if you get 24% yield, you need to convert that into tonnes. So what you need to do is consider what you'd get with 100% yield. Looking back at the part A of the question, we've already worked that out. So if 24% is 24 over 100, and then times that by the amount you'd get if you had 100%. So the total you'd get in this case would be 12.6. So the final part of this question, almost nearly there now, is the atom economy. So looking at the calculation, you'll see that 282 is the MR of C9H9O6Na3. We've calculated that before up in part A. Now the total MR of all the products, you have to include the mole ratios here, hence why I've done 3 times 46. So 3 times 46 is obviously 3 lots of ethanol, and you have to include all the products as well, so I'm adding 282 again onto that. So it becomes 282 over 420, times that by 100, and that gives us 67.1%. Okay, so now let's have a look at another example of a more challenging question. This time it's where you're needing to identify a certain product given titration data or some kind of reaction data. You have to try and deduce what the identity of the product actually is. So now we're going to look at how to work out the identity of a product from reaction data. The first part is going to be titration. Then there'll be a third typical example, similar to this one, but this time it'll be from percentage by mass data. And that should cover us for all the different types of more difficult questions, more difficult calculations, applied questions, in other words, that we might actually have. So you might want to pause the video at this point and just take a moment to copy this question down. It's an 8-mark question, and there's tons of information there to try and digest. So I suggest what we do is we highlight, and you can do this on your copied example, we highlight the information that we'll be using. So I know that I'll be using 2.580 at some point. I know that there'll be a connection somewhere between 25 centimeters cubed and the 250. So now what I've done is I've highlighted every single useful looking piece of information. I haven't even started to think about what I'm going to do with it yet. I've just highlighted it so my mind can be drawn back to it while I'm trying to work out what to do next. So the next thing it says to do is calculate molar mass. So I'm going to slightly change my colour, and I'm going to highlight it in a slightly different shade here, because what I'm highlighting now is what it wants me to do. Now I've just spotted one more thing. As I'm sitting here chatting to you, I've also spotted that as well. So what we're doing as we're going through is looking at little clues that the actual question is giving us. I've spotted something else as well. Formulae is plural. It means they want more than one to get the full 8 marks. So the other instruction they want to give us is to determine the molecular formula and possible displayed or skeletal formulae. So you might want to pause the video again here and just jot down what you think the important points to remember at this stage. What we have to do and what we have to use. Okay, to get anywhere near the molar mass of the acid, you have to work out what you have the moles of. And you have the moles of NaOH. You have the volume and you have the concentration. And because each molecule of A has one acidic hydrogen atom, that means that it will react with NaOH in a 1-to-1 ratio. So we can do a simple AS calculation, can't we, to work out the number of moles of NaOH. So I've taken my number of moles per decimeter cubed and I've times it by the average titer, 23.75, dividing that by 1,000 to convert to decimeters cubed. It gives me 3 times 10 to the minus 3 moles. Now we also know that that's going to be the same number of moles of acid as well. So not forgetting our mole ratio, we can now say that it's the same number of moles of acid, but that's only the moles of acid in 25 centimeters cubed. We obviously want to know how many moles are in the original 250 centimeters cubed, so we multiply that by 10. Now we also know that the mass of the compound A that we used was 2.580, and now we know that in that amount you have 3 times 10 to the minus 2 moles, so all we have to do is rearrange moles equals mass over mR. So here's the technique I'd suggest to work out your molecular formula. You know you've got one COOH group, so that's going to be a total of 45. So that leaves us with 41 to play with. So that leaves us with 4 carbons, including the COOH, and we know it's unsaturated. So what we can do now is work out what possible isomers you could have based on this idea. So I'm just going to draw them in. So you'd have 1, let's make it unsaturated like the question suggested. What have we got? We've got 1, 2, 3, OH. So how many carbons, how many hydrogens can we fit in there? We've got 3 carbons, let's do another carbon. So, another one there. So that's C4H6O2. So you basically want to do 2 possible isomers with 4 carbons in them. You have a carbon-carbon double bond and you have a carboxylic acid group. So your final criteria, bottom right hand corner, you need to draw 2 isomers. They both have to have carbon, double bond carbon, they both have to have a COOH group, and they both have to have 4 carbons in them. Doing that should get you the 8th mark in total. Okay, now this is one that's caused trouble for a lot of people over the years. What I'd suggest you do is copy down the question that's printed in blue, pause the video, and see if you can yourself highlight where the important information is, and then see if you can underline where the important instructions are. So in other words, what you need to do is take the question apart in your own mind as if you were doing it yourself. So it's 5 marks, so that would be 5 minutes to do it. I'm not saying to start it, I'm just saying to copy it down and either use a highlighter to highlight the data and underlining to do the instructions, or in some way differentiate between those 2 things. So when the video plays again, I'll have it done for you. So did you get the same as me? So let's now have a think about what each of these things means. Okay, so this gives us a little pathway to start along. We know that the mass data will allow us to work out moles. We know that the MR of eugenol is 164 grams per mole. And we know that our molecular formula will take the form CX, H, Y and OZ, where L, X, Y and Z are numbers. So the first thing to do is to start to work out the moles of everything. We've got three things we can work out the moles for, so let's do that first. So once we've worked this out, we can see something quite interesting, can't we? If you look at the number of moles of eugenol and the number of moles of carbon dioxide that was produced when it was burnt, you'll see that there's exactly 10 times as many moles of carbon dioxide as there are of eugenol. That would suggest that eugenol, each molecule contains 10 carbon atoms. So this is definitely something to keep in mind for later on. So what we're trying to get to, ideally, is the ratio of carbon to hydrogen to oxygen. The slight problem we have is that 0.051 mole doesn't go neatly into 0.0085. So simply just comparing eugenol with carbon dioxide and water is only going to get us so far. So what we've got to do now is think, how many moles of carbon do we have? How many moles of hydrogen atoms do we have? And convert those into masses, then the remaining mass will be oxygen. So for carbon, we can assume that the number of moles of carbon is going to be the same as the number of moles of carbon dioxide. So rearranging mass over mR, so the mass of carbon is the atomic mass times the number of moles. 12 times the number of moles of carbon dioxide gives you 1.02 grams. We can also do the same for hydrogen. Okay, this time we make another assumption, and this assumption is that for every mole of water you'll have 2 moles of hydrogen atoms because of H2O. So that's why the 0.051 is multiplied by 2. So the next thing we can do to get the oxygen is to work that out by difference, because we don't know from specific data how much oxygen has been used, but we can actually work out how much has ended up in the eugenol. So now we have the individual masses, we can work out the empirical formula, and from the mz value, or the mr, we can work out what the molecular formula is, and job done basically then. So this bit's easy. So right down at the bottom of the screen, you can see that we've divided the mass of each element by its atomic mass to get a ratio, and we've divided the ratio through by the smallest to get a whole number ratio of 5 to 6 to 1, so the empirical formula is C5H6O. Now if we look at the data for eugenol, we were told, weren't we, that its m over z value of its molecular ion peak, therefore its mR, is going to be 164. So if we work out the empirical mass for C5H6O, it's going to be 82, which goes into 164 twice, so that means the molecular formula would be C10H12O2. You simply multiply everything up as per normal. And there we have it. A little bit of AS chemistry, A1 chemistry, and a little bit of thinking, a little bit of deduction, and a little bit of bringing together all the information you've got. It's not that bad, is it? Okay, best of luck, and thanks for listening.